I'm Anupam. Today I'm going to give you the concept of Einstein concept of time dilation, length contraction and relativistic mass gain. Okay. Before going to do this, the velocity of light or speed of light is always constant c. Okay, but whatever speeds right now we are seeing, that is very less than c. Okay, but this concept is valid when the velocity is almost tends to c. Okay, let's say you are traveling with a train having a velocity 10 kilometer per hour and you are moving toward that direction. Let's say you're here. Now let's say you are throwing a ball having a velocity of 20 kilometer per hour. Okay, so let's say I am standing here stationary just beside the platform. Now I will define the velocity of this ball is 20 plus you are itself is moving 10, so 20 plus 10, that is equal to 30. Now if I have a similar situation, let's say you are in a train, let's put you in this box. Okay, and this time instead of ball you have shined a torch like this. This is a torch and a particle photon is going to that direction and velocity is c. Okay, and the train is moving with the velocity, let's say 10 kilometer per hour, and I am stationary and standing beside the platform, and I will see the velocity of this photon which is moving with the velocity c, and you are also moving with the velocity 10, so c plus 10 kilometer per hour. Is that concept is correct? No, this concept is wrong. The velocity of light or the velocity of a photon does not depend on the inertial reference frame. Okay, so I will also see the velocity of this photon is c, and you will also see the velocity of this photon or light is c, because it doesn't depend on the velocity of the reference frame. So now what is actually then varying? The varying is time. Okay, let's say I have created a simple light clock. Let's say this is my reference frame, that is x direction, and this is y direction. Y direction is this side. Okay, and I have a mirror like this here. This is a mirror and I put a mirror here also. Okay, now a light beam, let's say this one is light beam, is bouncing towards this direction to that direction, that is it is going to this direction. Here we have a mirror, it is reflecting from there, again coming back to this direction. Here we have again a mirror, it is again reflecting here and going to that direction. So it is just bouncing this. So it's a simple light clock. Okay, and let's say this reference frame has no velocity, and let's imagine another reference frame that is having a velocity. This reference frame is x prime and this having a velocity v. Okay, and it is moving to this direction. This is y prime, this is x prime. Okay, it's moving with a velocity v. Yeah, so you have a mirror again here. Okay, and this is the origin o prime. Here we also have a mirror. This is the light beam, it is again bouncing toward that direction and that direction. Here the time is t, here the time is t0. Okay, so since this one is moving, let's say after some interval this reference frame will travel here. Okay, so it will be here and the mirror is here. It is moving like this to that direction. After some interval, since it is moving with the velocity v, it will come in this direction. Okay, so again we have a mirror here and it is bouncing like this and so on. Okay, so now instead of this I will see, since this reference frame has a velocity v, I am seeing that light is taking longer path, that is it is going from that direction to that direction to that direction to that direction and so on. Okay, so I will see the light, the photon beam is taking longer path compared to this. So what is the path length? The path length is obviously the velocity of photon or light is c, and it is taking a time t here with respect to this reference frame. So this path is c into t, ct, and since it is having a velocity v towards that direction, so this path will be v into t, vt. Now here the movable reference frame having its local time is t0. So here what is the length of this path? So you have a velocity of photon is c and time is t0, so this path is t0. So now this is a right angular triangle. This length is pi by 2 or 90 degrees. So this is a right angular triangle. So we can apply the Pythagoras law, that is ct whole square, that is equal to vt square plus c 0 square. Okay, so from that we can derive see, we can take common, and we have sorry, I can take t as common, then we have c minus v. Okay, and we also have here c square, t0 square. Okay, these all are squares. Okay, from that we can derive that t is equal to t0 into root over 1 minus v square upon c square. Okay, now this term 1 minus root over 1 minus v square upon c square, this is a special term. It is denoted as gamma. Now from this equation we can derive the value of gamma lies between 1 to infinity. When it belongs, let's have a chart. It depends on velocity gamma. Let's say from this equation, carefully observe, if I put v is equal to 0, if v tends to 0, I would like to say, so it is very close to 0 but not equal to 0, then this term vanishes, only 1 comes here, so the value of gamma is 1. Okay, so I would like to say gamma tends to 1. Now if v tends to c, the velocity close to c, then this term becomes 1. So 1 minus 1 is 0. So when the denominator becomes 0, this value becomes infinite. So gamma becomes infinity. Okay, so in our normal life, v is very small. So this term is almost equal to 0. So in normal velocity, in normal terms, gamma equal to 1. So we don't understand the time dilation. Okay, but if our velocity is very close to velocity of light, then we'll understand what is time dilation. From this equation, if I put 1 upon root over 1 minus v square upon c square is equal to gamma, then we have the equation like t is equal to gamma t0. Okay, so this is known as time dilation. Okay, now from this equation, if I put t is equal to, let's say t is equal to, since we have a formula like v is equal to s by t, it's a very known formula from us. Velocity is equal to distance divided by time, v equal to s by t. From this equation I can derive that t is equal to s by v. Okay, so if I put similar kind of thing, let's say t equal to s by c, c is a velocity of light, is equal to gamma times s0. Since from t0 I am writing s0 because the length will be different relative to me, so s0 by c. So now we can cancel out this term because c cancels from each other. Then we have another equation called S0 is equal to gamma S0 equal to S divided by gamma, or we can write S is equal to gamma times M0. So this is our length contraction equation. Okay. Now let's say in this reference frame, where the if a particle, let's say a particle M is moving towards that direction, having a length, this thing, from this particle having a mass m0 and the length is L, so this particle is moving from here to here. So let's say this inertial frame having a velocity v, okay, then and also it is moving with a velocity u, okay. So now we have m0 into u, that is our momentum of this particle, okay. That is equal to, this is the mass of this movable inertial frame, is equal to the mass at with respect to me, that is m, that is equal to m into u, and the frame is itself is moving with a velocity v, okay. So u plus v. Why I have written equal to here? Because of the theory of conservation of momentum. Since the momentum of this particle is same in both the reference frame, irrespective of the velocity. So if I write this, I can also write from this equation, I can write m0 equal to L by C. Here also I can write m is equal to u plus v, I can write again L by C, okay. Sorry, m0 is equal to L by T0, and here I can write m0, m is equal to L by T, okay. So this time are different, okay. This is the time at the rest, and this sorry, not one, this is the time with respect to me, okay. Now from this I can cancel out these two terms, okay, and I can write, this is not nothing, so T is equal, from this equation I can write T is equal to gamma times T0, so I can write m0 by 1 upon T square, T0 is equal to m is equal to 1 upon gamma times T0. So from this equation this T0 cancels out, and if I put gamma to this side, I have m is equal to gamma times m0. So this is relativistic mass gain. This is equation number 3. From here I can understand the value of gamma lies between 1 to infinity. So if the velocity is very less, then the gamma is equal to 0. That means both local mass and relativistic mass is same if gamma is equal to 1. But if gamma v tends to c, the velocity goes close to the velocity of light, then gamma tends to infinity. That means though our local mass is same, but the relativistic mass becomes infinite. So that's the reason no matter can travel with the velocity of light, because its mass become infinity. Only massless particle, let's say photon is massless, that only can travel at the speed of light. So that is the concept of Einstein, that is time dilation, length contraction and relativistic mass gain. Hope you have enjoyed this video. If you have anything, then please write to the comment box, and thank you very much.